This is an SDR-IP. I will connect it to a computer with Windows 7, calibrate it with this function generator. This is how the SDR-IP is configured. This is the spectrum of the TTL output of the function generator. I can press max hold and we can see that the spectrum is far from flat. The entire spectrum is 20 MHz and we want to calibrate a bandwidth of about 2 MHz. So it means it should be flat to within well below 1 dB over one division on this, and it is not. With a capacitor in series like that, the spectrum is now more or less flat. Can press max hold again. The signal is quite a bit weaker, but it is flat to within a tenth of a dB or something, more or less from 2 MHz to 20 MHz. There is one problem, however, and that is every second pulse is weaker. So positive and negative transitions have different rise times. And this could be a problem in the calibration of Linrad. We will see. The SDR-IP uses the network. There is no installation procedure for the hardware because the network is already in place. I start Linrad as an expert because I want to use the second time function oscilloscope to demonstrate how successful the calibration is in terms of making the blanker work well. Here I will calibrate with the function generator and then verify with the proper pulse generator. So expert E, and this is a large screen, so I can make 2, and I don't need any priority. Set timer resolution, just go for the default, and no auto start, and I specify the screen in pixels. Let's make it 1400 by 800. Click on the window to get its focus and then press W to save the parameters we have so far. Now go to the input and output setup, that is U, and then A to select something for the input, and here it is SDR-IP, that's D. And for some reason the default is the address that I have myself. So I don't change the IP address, I don't change the port, I just connect to the SDR-IP with C. Something went wrong. I have to connect the network cable also. now it's connected. And use this hardware? Yes. I could have more of these units and run other instances of Linrad with them. Set the global parameters. The rate dividend, the smaller I make it, the faster sampling speed I will get. I want to select a small rate dividend, that's A, and it goes from 6 to 250, so I make it 6. And that gives 1.3 megahertz sampling rate. I could change B to have 16 bits per sample, and if I do that, I get A all the way down to 4. And I prefer to do this. UDP packet size, that has some influence on the latency. And Vitter should be on, that is D. And normal input and save, that is X. And then something for the output, B, and no port audio. I think 2 is where I have my loudspeakers. Try that. What comes in those lists depends on what operating system I'm running, and I have too many and I cannot remember. Anyway, now it's saved. So let's go for calibration. I can make it in SSB mode, that's D. So I'm prompted to the parameter selection because there are no parameter files yet. And I enable the second FFT because I want to demonstrate the noise blanker a little bit later. But the other things I just accept the defaults. And I rearranged the screen a little bit. Because the second time function oscilloscope will be in a fixed place on the screen. Sorry. It's better to put this here because I want a large range on the dB scale on the S meter. And I want it as a dB scale, actually as a dBm scale. The blanker is running, it's just the dumb blanker. I change the scale for the waterfall and right click there. This is what we have. I can switch off the function generator, and we see that the interference was much lower, but there is no difference in the waterfall. The dumb blanker is effective also because there are no strong signals here. The threshold is a little bit too low. This is, I enable the oscilloscope and reduce. You can see that the noise is only maybe 5 bits peak to peak. with the function generator running, you can see the pulse is cut away completely and the noise floor is not affected. If I change the scale, disable the blanker and change the scale, this is what the pulse looks like. And the level here and I don't want to see the peak, I just want to see the RMS noise. Is the yellow track. The noise floor without the signal generator is very low. I place it there, and then with the pulse source we are very much higher. It can be convenient to put minus 79.5 here. So we know where the noise floor is. It is of course not 0 dBm. I use the dBm scale with some odd calibration value here to put the noise floor at the 0 point. And now I can switch on the function generator and see I have 32.5 dB now, and that is with a pulse frequency of 360 Hertz. Now it's time to do the calibration. That is X, C, B, and this is the way the pulses look. The upper is power in a logarithmic scale, the lower trace is I and Q in linear voltage scale. I can change the gain. I press plus 4 times, for example. 1, 2, 3, 4, 5, 6. And you can see that the pulse is surrounded by oscillations. This is typical for a digital filter, for a finite impulse response filter. I press enter, and now Linrad starts to collect pulses. The magenta is the power, and the green is the second derivative of the phase. And it is power and phase as they come from the Fourier transform. The reason that it is the second derivative of the phase is that the phase itself varies from pulse to pulse and cannot be averaged. The first derivative is also varying, but the second derivative, that is always the same for all pulses, so it is possible to take the average of that. To have a look at this curve, I press plus to magnify, plus, and you can see there is something here. This is an artifact. Plus, plus, plus. And there is a small artifact there as well. The reason for this is that Linrad takes the pulses one by one and cuts away what is at some distance away from the pulse. And that is the same as a high-pass filter. It means the DC component is removed. And for that reason there is a discontinuity here at the center. Now I have 50,000 pulses. I've been talking too long. but there's no harm in that. You to compute a new filter. And this is the default that Linrad suggests. You can see that there will be a little bit more gain at the band edges, and that's because the gain in the SDR-IP is lower here and here, and for that reason Linrad has to apply a higher gain. So accept the default. Why? I will show later on what happens if you don't use the defaults. That will save to disk from RAM to apply this calibration. X and B to go back till SSB mode. I select the frequency and then apply the smart blanker. And you can see we are back at roughly a normal noise floor. I can switch off the signal, the function generator that gives the pulses, and it has, you can see that the blanker isn't perfect. There is some noise out here, but in the center region where I am now, the blanker is nearly perfect. I can run the, oh, it's already running slow. If you look at the S meter here, I switch on the pulse again. And it doesn't make a difference. But out here, the noise level is a little bit more than 4 dB higher. Here, when I switch off the pulses, it is nearly 3 dB higher. And the reason is, of course, that the gain of the SDR-IP is lower, which Linrad compensates for, and the consequence is a degraded noise figure out here. The noise figure is nearly 3 dB worse. So now, when I switch off the blanker, the pulses are this high. I reduce one step further to be sure that this point is not saturated. The saturation is somewhere around up here. The pulse is now about 10 millimeters on this screen, and I apply the blanker and increase the gain in steps of 6 dB. 6, 12, 18, 24, 30, 36, and now it is 5 millimeters, so one more, 42 dB. The attenuation is 42 dB on these pulses. And I could enable also the dump blanker, like that, and bring the level, the threshold down a little bit. And then you see there is not much noise anymore. I switch off the noise source. Here you can see a little. Switch on the noise source again. Now running only the dump blanker, you see it cuts a fairly large hole in the signal. There are some artifacts, but most of the spectral region is perfectly okay. The pulse repetition frequency is 720 Hertz because the generator is at 360 and it's a square wave. So this is what we have, and now I will go and do the next step of the calibration. X, C, C, and 900 Hertz is excluded from the center in both sides, but since the pulse repetition frequency is 700, I need to make this region a little bit bigger, because the filter that removing the DC in the procedure of calibration, that has a corner frequency a little bit higher than this. Let's make it, this is not very critical, but let's make it 4 kilohertz. This is new in this version of Linrad, that you can also set how far away from the center one should fit a curve. Now it is 500 kilohertz, and I have to reduce that for reasons that will be obvious later. R, and I make it 150 kilohertz, like that. And then continue. And I press plus, plus, plus. The yellow curve is the measured data, the raw data. The red curve is the fitted data. It is fitted from here and out to the green line. And you can see the discontinuity is out here. I can press right, R, and then use what is at the right side of that blue line. Put all those points to 0 on the red curve, which means eliminating these points and that point and put them here. So accept, that's A, and then R, I do the same here, even though I don't really see any discontinuity. Accept. Here we have undulations. That's the reason the limits are set so that the curve is fitted only from here and out to the green line. Because I am only fitting a polynomial, and this undulation continues all the way, and one cannot fit a long sine wave well with a polynomial. But the fit is not good enough. I increased the number of terms to 9 and more gain. This looks fine. R, and then accept, and then R, and accept. Now the center discontinuity is gone. I press S and then go back. And look at the signal here. I switch off the signal generator. The influence of that discontinuity was very small, so it wasn't really important to do that step. Now with both the clever and the dumb blanker, the total blanking is next to perfect. I switch off the pulses and switch on the pulses. You can see there is something out here and out there that comes from the dumb blanker. There are signals in the passband. I can try to not route them through the blanker by bringing down here. And now there are red dots at some points here, also here, and all those signals are visible here. Maybe I went too far. Let's make it like that. And switch off the interference. I have to bring, here you can see the signals, the red things. To show some other phenomenon of the calibration, I bring up the scale on the spectrum here and change the frequency. It's now 7 megahertz. I go up to 8 megahertz. And I have to bring that up. And you can see the calibration is no longer good. If I remove the dumb blanker, you can see that the smart blanker is no longer very good. Uh, 1 megahertz away, the frequency response is quite different. I can put 0.05 here to step the frequency in steps of 50 kilohertz. What's this? Aha. When going from 7.0 to 7.05, there is a filter that switches. I can hear the clicking sound from the SDR-IP. If I go in the other direction, the difference is much smaller, but you can see that the spectrum changes and that the blanker deteriorates. So it's calibrated for 7 megahertz. This is a proper pulse generator. It has a 555 here that oscillates at a frequency that can be set by the switches here and the potentiometer. It's just a standard circuitry for the 555. It's followed by a 74 AC 74 that divides the frequency by 2, and by doing that the pulse length is ensured to be the same for positive and negative halves of the square wave. Then there is a 74 ACT with all the 6 inverters connected in parallel. And then there is an output, a capacitor and the resistor to ground. That is to convert the square wave to a train of pulses where every second is positive going and every second is going negative. That doesn't matter for the calibration, which sign the pulse has. The pulse length is about 10 nanoseconds. The capacitor is 220 pF and the resistor is 100 ohms. It's of course in parallel with the impedance of the cable, which is 50 ohms. So the calibration was done with this function generator, as you see it here, with a capacitor in series, and then the pulses look like that. They are about 2 division from the bottom. The proper pulse generator looks like this. These pulses are about 20 decibels stronger. I have done the calibration with the function generator in a way that isn't really correct. That is because I wanted the strongest possible signals, so it would be possible to study the small remainder that we have when the blanker is running. But there is an error, and that is that the impedance, the input impedance of the SDR-IP is not 50 ohms. And feeding it through a small capacitor means that the signal varies with frequency. I can make the impedance close to 50 ohms by inserting the attenuator here, 10 dB, and I have to go up 10 dB here, of course. And you can see now the calibration is not so good anymore. The proper generator is close to 50 ohms. I have an attenuator between it and the SDR-IP to guarantee that. And therefore I have to recalibrate with the function generator to get it properly calibrated for a 50 ohm system. It will not be possible to see so many details because the pulses are weaker. But anyway, X, C, and this is the usual B. And here are the pulses, enter, and clear what we have, that's A. And you can see now that the frequency response looks better. It's more flat. But there are errors, you see. This jumps up and down. That is because the signal to noise ratio isn't good enough for the pulse train. To fix that, X for exit, go back, calibrate, and B. And now I run the frequency higher on the function generator. I have set it to 1.1 kilohertz, so we get 2.2 kilohertz in pulse repetition frequency. Hopefully this will go better. I pressed enter again, and then we see here. And I have to clear the RAM again. And now it looks okay. And it collects pulses very fast now. And these pulses are weaker, so it's good to take a little bit larger number of them, but it goes very fast. I have 20,000 already, and that's going to be enough. So U, and accept this. You can see it is much flatter than before. The yellow and the white line are very on top of each other, except here. Y, accept, and save this, and X, and back. And now this looks a little bit, there are structures. That's because there are more than one pulse in each Fourier transform, and the separation between the pulses generates some structure here. Click on the signal. Oh, looks good. And of course, the noise level is high, but that's because there are so many pulses. Each pulse is not as high as before, and you can see there are lower now. But the calibration is now reasonable. I check by going down 10 dB more. Sorry. And you can see another 10 dB attenuation does not change the frequency response much, but if I go up to 0, there is a problem. Strong mismatch changes the frequency response. Now I will connect the proper pulser. Here I have attenuated the pulses from the proper generator by 18 dB to get them to the same level as I had before when calibrating with the function generator. The pulse repetition is the same, 720 Hertz. And you can see that the remainder of the pulse is a little bit higher, but not much. I switch off the pulse generator, and you don't see any difference on the S meter. If I go up here where it is worst and switch on the pulse generator, you can see I have lost 2 dB in signal to noise ratio with these fairly brutal interference. Now I will calibrate with these signals instead. X, calibrate, B, and enter. And I had a problem. I don't see the wiggles, and that is because I forgot to clear the RAM memory from the previous calibration. I will do that. A. It doesn't really matter. I could rewrite on the old calibration, but this is what we actually observe from the hardware now. And it's obvious the gain is higher here and a little bit lower here. The shape of this is different from before. And this can be enough, so I press U and again Y and save, that's S, and X and B. So this should be similar to what we had before, but if you look here, it looks better. Occasionally pulses are completely gone. Now I can make the pulses 10 decibels stronger. I go down here, 10 decibels. And select the signal here and disable the blanker, and it's over 40 decibels at the pulse repetition of 700 Hertz. So now I go for the second stage of the calibration. X, calibrate and center discontinuity. I make the L limit to, I don't remember, 3 kilohertz maybe, and the width, that's range, R 150 kilohertz, and continue, and plus, and I want to get rid of these things. A to use that, and then R again, and A, and here I need more terms in the polynomial fit, so I press 9, and 9 was enough. R and A for accept, and R and A to accept, and then update with S and go back B. And click somewhere. And I don't remember exactly how it looked, but when it is on the video I can go back. I think it should be a little bit better now. I can switch in the attenuator, and the calibration is still good. The impedance change doesn't matter much now that the pulses come from a proper 50 ohm source. So I go back up here again and switch off the pulse generator. And remember, the pulses are now 10 dB stronger than before. And this is as good as it gets. If I enable the dump blanker, it becomes a little bit better. If you are on VHF or microwaves with a very well-defined frequency response set by converters that are in front of the receiver, you might want to calibrate a little bit differently. I will show that. That would be X and calibrate and B and enter. And now first clear away the old calibration, collect the data, I will select a different shape on the filter that Linrad implements with this correction procedure. And I will wait for a good statistics also this time. And 18,000 is good, so I press U. And now I change the shape on the fall off here. It is now the Gaussian error function, but I change it to a parabolic function. And you see the flat passband is now much smaller. It's only from here to here, and I can make it a little bit even smaller. Decrement steepness, that's F, like that. Accept with Y, and then save S and X and back B. So you see we have a narrower frequency range, but it's still well above 1 megahertz. I switch off the pulse generator. It doesn't make a very big difference. This makes some difference out here. And I switch it on again. And do the second step of the calibration. X, C, C, and L and 4000. With a pulse repetition frequency of 700 Hertz, it's reasonable to make this somewhere in the range 2 to 4 kilohertz. And then I change the range to include in the fit to, that's R, and to 150 kilohertz, like that, and continue, and plus, 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 plus. I am going to remove these points to place them at 0. That is R, and accept A, and R, and A. I need more terms in the polynomial fit, so I press 9, and that's enough. R, and A, and R, and A, and S to save, and B to go back. And again, switch off the pulse generator, and the difference might be a little bit smaller than before, but it's not a big effect. Switch on the dump blanker, like that, and it adds a lot of noise out here, outside, well away from the passband. But within the flat region, the switching off the pulse source or switching it in does not make nearly any difference. Listen to a station. I don't know what it is. It's probably a carrier from the AM of some kind. And then switch off the blankers. And that's quite a lot of interference. On microwaves, it might be interesting to have the widest possible flat passband. That's arranged like this: X and calibrate, and B, and enter, and A to remove the old calibration, and wait for a while. Now these pulses are very strong, so very good statistics are obtained fast. It's still running with 700 Hertz for the pulse repetition frequency. And this will be enough. I press U, and then I make the flat region larger. That's by pressing A. Now we have about 4 dB extra gain at the edges. You can see that here. Further than this is not reasonable to go, because the noise figure will drop by these 4 dB at the edges. Accept, and then save, and X, and go back to the processing screen. And you see we have from here, that's 6.056 to here 6.066 minus 7.946 equals 1.88 megahertz. Perfectly flat passband to within better than 1/10 of a dB. I will try to see how flat it is by making the gain of the dB scale higher. So this looks to be flat within much better than 0.1 dB, more like 0.01 dB. And the noise blanker is probably not quite as good. I enable it, and then switch off the pulse generator. I'm out here. At the center, it's better. Actually, very good.